Okay, hello everyone, and welcome to part 2C of sugars and nucleic acids. Today we're going to talk about the chemical synthesis of oligonucleotides. So this is part C. We just talked about biological synthesis, and now we're going to think about the chemical synthesis. As you can imagine, this is going to be a little more intensive compared to biological synthesis, because if you compare what we learned with peptides and proteins, the synthetic or the chemical synthesis of peptides, we had to use protecting group strategies so we could orient the right nucleophile and electrophile. So we're going to have to apply the same mindset when we're synthesizing oligonucleotides chemically. All right. So chemical synthesis of oligos. So as I mentioned, it's a challenge. Many different functional groups present. Got to use different types of protecting groups. We can automate the synthesis. Okay, there's a lot of really great automatic synthesizers out there, and as you'll learn, it's a much more complicated process compared to peptide synthesis. What this has done, though, this has really allowed for technology to get developed really back in the 80s and 90s to allow molecular biologists to create and make oligos made by machines. So we were talking about short oligonucleotides last time, things like primers, things that are necessary for PCR, things that are necessary even to induce transcription or DNA polymerization. You need to have these short primers, and these are all made by short oligos made by a machine. So they're really quite efficient. Similar to peptide synthesis, we use solid phase beads. They're a different type of bead. They're not a polystyrene bead. They're actually a controlled pore glass bead, but the analogy is the same. What this allows the researcher to do is it allows them to wash with reagents, solvents, etc., in order to get a desirable product with minimal purification between all the steps. Okay, so let's think about how we can couple deoxynucleotides to one another. And let's think specifically about what we learned with polymerases. All right, so with polymerases, let's mimic what biology does. And biology does synthesis in the 3' to 5' direction. Okay, so meaning that if this is a dinucleotide and we're creating our new bond, we're creating an oxygen phosphorus bond right here. So let's recreate what biology does. We had a 3' hydroxyl group. That was a good nucleophile. And we had some type of electrophilic phosphorus. I'm just putting arbitrary R1, R2 groups. At this point, it's not super important to know what those are, but you can see here that we have our nucleophile. And here we have our electrophilic phosphorus. So as I mentioned, this mimics biology, and then you can imagine that this would come and attack this phosphorus, and that would be what's necessary to create that oxygen phosphorus bond. Okay, so that's a very logical first step, and in fact this is what was done back a long time ago. This is also known as the Corona synthesis of DNA, synthesized in the 3' to 5' direction. So in this instance, the researchers designed a 3' hydroxyl, and then they had a phosphorus group here, a phosphate group that had a good leaving group here. So that's a good electrophilic thing. So you can imagine a whole bunch of different types of leaving groups. You would get this oxygen attacking to form a tetrahedral, or in this case a pentahedral intermediate. Electrons come down, release off a leaving group, and then you'd be left with your phosphate ester. Okay, they have to use protecting groups. So we've learned already the acetyl protecting group, so that you wouldn't get cross reactivity, or you wouldn't get this OH group reacting with another molecule of itself. So after they treated that acetyl group with sodium hydroxide, they could now have another 3' hydroxide, and then this could, you could do this reaction over and over again. So this reaction, looks really good on paper, and if they did the reaction, they actually observed around an 80% yield per coupling. And if you think about that, maybe that's not so bad, right? If you go into your organic chemistry lab now and do a reaction to get 80% yield, you feel pretty happy. That's pretty good. And I would be very happy as well. But the issue with oligonucleotide synthesis, and like we also learned with peptide synthesis, is that if you're trying to make something that's more than 1 or 2 units, for example, a 20 mer, like a 20 mer oligonucleotide, you need to take that yield. In this case, it's 80%, so 0.80 times 20 steps. And if you do this 20 times, your overall yield is going to be 0.0115. Translate that to a percent, that's around a 1.2% yield, overall yield. So that's really not so great. You get low overall yield, and then therefore, because of that low yield, purification is going to be very challenging. So this was tried and attempted for a while, and really there wasn't much optimization done in this time. To date, there have been advances going from 3' to 5' direction by some researchers and companies, but we're talking about research that was done in the 80s, so this was largely abandoned, and this really made chemists think about how to synthesize DNA and go back to the drawing board. So what we looked at before was scenario 1, 3' to 5' direction, but researchers thought, well, instead of making this the key oxygen phosphorus bond, what about making this the key oxygen phosphorus bond that's being made? I mean, ultimately, at the end of the day, the DNA molecule or RNA molecule really shouldn't care. So if that's the case, let's reverse what the electrophile and the nucleophile might look like. So in this case, you're going to have base 2 that has a 5' hydroxyl group, and you're going to have a phosphorus group here that's attached to a 3' oxygen. Okay, so this is 1, 2, 3', 4', 5', 1, 2, 3, 4, 5'. So this is now your electrophile, and this nucleophile is now actually a primary alcohol compared to the 3' hydroxyl that we saw earlier. So this primary alcohol really should be more nucleophilic and react much better compared to a 3' electrophile. And it turns out that after years of optimization, that this is now the gold standard in terms of how oligonucleotides are made chemically. So whereas enzymatic synthesis goes from 3' to 5', the universal way to synthesize oligonucleotides actually goes in the reverse direction, so the 5' to 3' direction. Okay, let's take a look at the chemical synthesis of these building blocks. And what researchers use are these really funny looking molecules that I've seen here. And you might say, well, that looks nothing like a nucleotide or nucleotide triphosphate. And yes, I agree it doesn't, but there are certain common elements that I hope you recognize that we'll go through, and other protecting groups that or similar protecting groups that you've seen before. Okay, so let's identify each protecting group in each area one by one. Okay, so we have this, remember we have 1', 2', 3', 4', 5'. We have this oxygen here. So this is naturally a 5' hydroxyl group. And then what we've attached here is a trityl group, right? It's a trityl group that we've seen in peptide synthesis. The only difference is that there are 2 dimethoxy groups. So we call this dimethoxy trityl group, or abbreviated DMT or DMTR, dimethoxy trityl group. And as you might imagine, dimethoxy trityl groups can be removed with weak acid. In fact, something like 3% trichloroacetic acid is enough to break this oxygen-carbon bond to generate a positive carbocation, so that you can now have your 5' hydroxyl group. Okay, so that's one group. A second group is this group here, which is called a benzoyl group. And what it does is that it protects the exocyclic amine of heterocycles. So before this adenine got protected, it looked like this. I'll just put our group there. And this adenine NH2 group here is an undesired nucleophile. So we need to find a way to protect it. So benzoyl group actually is a very efficient way to do so. And it protects the exocyclic amine. All right, so we have 2 different protecting groups so far. And then the last group attached to this is this group here. And we talked about the phosphorus being electrophilic. So this is an electrophilic phosphorus. There's a couple different R groups attached. We call this a phosphoramidite. Very electrophilic in the presence of acid. Attached to this phosphorus is this group here, which is an O oxygen, O cyanoethyl, so 2 carbons, O cyanoethyl protecting group. And this protects the phosphorus. It also protects the oxygen from the phosphate backbone from reacting. So it acts as a protecting group as well. Okay, so that's your basic building block for chemical synthesis. Let's take a look at how we can actually synthesize these DNA building blocks from general deoxynucleotides. Okay, so here you have adenine, here you have guanidine, here you have cytidine, here you have thymidine. So how can we actually transform and make those? All right, so the first thing we're going to do, let's just start with adenine, is we're going to take adenine and we're going to treat this and protect the exocyclic amine first. So we're going to treat this with benzoyl chloride and some kind of base. Okay, so you can imagine the nitrogen will come attack, electrons go up, then come back down, release off the Cl minus. Once that's done, then you're going to install the dimethoxy trityl group at the 5' position. So what we're going to do is we're going to take dimethoxy trityl dimethoxytrityl chloride with base, and via SN1 reaction, you'll get installation of that group. Okay, so if I just flip the page for a second, this will bring you to this compound here. So two-step process. And then from here, we can now take our remaining 3' hydroxyl group and create our phosphoramidite. So this would be step 3, and this would involve taking this chlorophosphoramidite So you can buy this reagent here. You can also synthesize it, or just buy it because it's easier to do so. And then you can see that it's SN2 chemistry. So what you'll end up making is your adenine phosphoramidite with a protecting group at the exocyclic amine, as I'm drawing right now, in addition to dimethoxytrityl group at the 5' position. Okay, so that's how you make the phosphoramidite for deoxyadenosine. Now, let's just go back because we have 4 other bases that we need to deal with as well. So you can see here that with guanidine and cytidine, you also have this exocyclic amine. With thymidine, you don't actually have an exocyclic amine. So you don't need to worry about using benzoyl group on this molecule here, but these ones you do. So for these ones as well, you're actually going to do the same type of chemistry. All right, so I'll just kind of lump these together and say I'll use the abbreviation for benzoyl group. It's BZ chloride or BZ chloride, and then 2 DMT chloride and base. Okay, so you bring that up to your next slide, and then these are the 2 different monomers that you have. All right, now if we look at thymidine, you don't need that exocyclic amine. All you need to do is protect the 5' hydroxyl group. So it's actually a little bit easier. All you need to do is start with thymidine and immediately just add dimethoxytrityl chloride with base to afford this compound here. And therefore, once that's done, you'll make the phosphoramidites just like we did with the adenosine. Okay, so all of these things will come together, well, separately, but they'll all use the same reagent. Okay, so you can have now your DMT protected guanidine and it's it's good practice to to draw these out. The more practice you have drawing structures, the easier it gets. And then always inspect your structure to make sure that double check, make sure you haven't added any extra carbons or you aren't missing any bonds. Okay, for the next one, the cytidine. Here's our phosphoramidite. And then we'll take the cytidine and add that benzoyl group. Like that. And then finally, the thymidine. Will look like this. Okay, so welcome to your new phosphoramidites. Okay, so now that we've learned how to make these, they are robust. We can store them for many months in the freezer, and the chemistry to make them is really quite established. The synthesis of DNA phosphoramidites, over the years, the price has gone down in price, which is great because this has allowed for sequencing to occur really rapidly and in a cost-effective fashion. You can also purchase these precursors relatively cheap. We're just talking about a few dollars per gram in some cases. So what this means is that you can really streamline this synthesis and just start with the building blocks in order to make DNA. Okay, so that's what I use in my laboratory. Okay, so let's look at the solid phase support that is used to start making our oligonucleotides. So this is called a controlled pore glass, and it's analogous to the polystyrene beads that I was talking to you about, except that it's not polystyrene, it's actually made out of glass. And what you do is the glass is actually a polymer of silicon dioxide. And what's done is during that synthesis of the glass, instead of adding strictly silicon dioxide, there are these functional groups, the silicon triethoxide, which also has an amine attached to it. And these are interspersed so that now you have your glass bead that now has an amine derivatized attached from it. So it's similar, like I said, to the peptide bond synthesis in which we had an amine. Now, in order to start synthesizing, what we do is we treat this control pore glass with this precursor here, which is a DMT protected sugar with your base. There's a star here because it could be any of the bases, and there could be an exocyclic amine based on what it is. And then this group here, you have an oxygen, you have an ester, and then here you have another ester, but attached to this ester is a phenyl group with a nitro group, which is an electron withdrawing group. So it turns out that this leaving group here is much better, making this more electrophilic. So when your nitrogen comes and attacks, electrons will go up, form a tetrahedral intermediate, then they'll come back down, and you'll get a good leaving group. So what you end up having inherently is your control pore glass linked together through a stable amide bond, and then this is linked through an ester here. So you can imagine now if you want to create your DNA synthetically, what you need to do is remove that dimethoxytrityl group to have a 5' hydroxyl group as your strong primary alcohol, and then that will react with a phosphoramidite. So we're going to go through each step one by one. So I'll just write this now. It needs to be removed to make our desired 5' OH nucleophile. Okay, so step one is called detritiylation. So this is where we take our group here and we treat this with 3% trichloroacetic acid. So this looks like this. Actually, I'll put the chlorines like this. I think that's better. Trichloroacetic acid, and what that will generate is this. And I'm not going to draw, this linker each time. Okay, so I'm just going to immobilize it like this, and it's understood that it's attached to a solid support. So let's talk a little bit about how we now do our next step, which will be activation of the phosphoramidite base 2 with tetrazole. Okay, so here's our phosphoramidite. Okay, so now we're looking at base 2. We got to get this ready for coupling. And I told you that this is electrophilic, and it is electrophilic. And let's call this, you know, a good electrophile. But it's really a much better electrophile in the presence of acid. So tetrazole is actually a fairly weak acid, and your nitrogen electrons will come and will pick off that proton. So once that happens, you now have a nitrogen with a positive charge. So this is now, let's call this a very good electrophile. So we're raising the bar in terms of electrophilicity. Okay, now you have this tetrazolide anion that was made during this conjugate, during the acid-base chemistry here. And so what can happen now is that this negative tetrazolide will come and it will attack this phosphorus, which is, as I said, a very good electrophile, and release off this diisopropyl amine. So what you end up having just forgot to write base 2 here. You have this tetrazole attached to this phosphorus group, and this is actually now an excellent electrophile. You have a very good stable conjugated leaving group, and let's call this an excellent electrophile now. So in other words, this is now primed and ready to be attacked by a nucleophile. All right, so the next step is going to involve coupling of this tetrazole phosphoramidite with the 5' hydroxyl group from step 1 that we deprotected. Okay, and this is what this looks like. So we've made this phosphoramidite, as I mentioned before, relatively stable, mild conditions for synthesis, high selectivity for activation. So now you're going to get this hydroxyl group that we've already deprotected, and this is going to come and just react very efficiently. And then you get proton transfer from the oxygen, or from the oxygen. And this, you know, you can get really good yields. You can get yields from 99 to 99.9%. Okay, so it's highly efficient. And as you know, if you're making oligomers that are 20, 30 mer nucleotides in length, you need to have very good yields. Okay, there's your CPG. So we've created that oxygen phosphorus bond in the 5' to 3' direction. There's our new chemical bond. So congratulations, you've made that new bond. However, we're not done yet. All right, so what we need to do is we need to, first of all, understand that this is a phosphite. We need to find a way to oxidize it to the natural phosphate. So phosphates look like this. Okay, that's what nature uses. So we need to oxidize it. We need to find a way to remove this O-cyanoethyl group. So there's a number of different things we still have to do. We got to remove it from the resin, remove protecting groups. Okay, now before we start to oxidize it, I'm going to introduce a new type of step that you haven't seen before, and this is called a capping step. And this capping step is done more like insurance. You can think of this like insurance. So the last step I said was, let's say 99% yield, the coupling step. That means that 1% didn't react. Okay, so let's just say 1% unreacted. So this capping step, what this does is this says, well, you know what? We don't want that 1%, as low as that number may be, to react with phosphoramidite for base 3 or base 4, base 5, because we don't want to get mixed sequences, and this would really complicate purification. So after that coupling step, we rinse and wash, and then we take any unreacted 5' hydroxyl groups after coupling and react this with acetic anhydride and typically with pyridine. And what that will do is this will cap and make that 5' hydroxyl group acetylated, essentially making it dead so it cannot further react. Okay, so this step is important so that mixed sequences do not get generated. Okay, you do not want B1 reacting with B3, B4, etc. Okay, so you can imagine if you're doing multiple couplings in a cyclic form and there's always 0.5% or 1% that don't react, those become further threats to react with other phospharamidites downstream. So as I mentioned, it's not like it's important, it's not super essential, and it's more like insurance. Okay, the last step is that oxidation step that I mentioned. So this is where we need to take this phosphite in the 3-oxidation state, and we need to oxidize it to a phosphate. And this is done using iodine, water, and pyridine. Okay, so let's see how this happens. So I2 actually is a fairly large molecule, and inherently it can have, it's a large molecular cloud, and you can actually inherently have areas that are partially delta positive and partially delta negative. Okay, these can kind of fluctuate back and forth, and you have therefore a good leaving group within that complex, within itself. And this really only works, this works really well with I2 because of its size. So what's going to happen is that the phosphorus electrons from the phosphite will come and react with the I2. Okay, so what that will generate, and I won't draw this whole thing, I'll just draw a snapshot of that phosphorus cross-section. What you have is now phosphorus that's positively charged with a good iodine leaving group attached. Now we have water and pyridine. So I'm just going to draw water in this orientation here, and I'm going to draw pyridine. Okay, and pyridine is a good, it's a good base. It's a good proton sponge. You can do this over 2 steps, or you can do this over 1 step like I'll do. So pyridine, you can imagine it acting as a base, removing a proton from the water, and then simultaneously analogous to a hydroxide attacking through the oxygen. You'll get oxygen attacking the phosphorus, releasing off the I group. positive on the phosphorus. Okay, so we still have our positive on the phosphorus. We have the oxygen attached. That's our source of oxidation. We've added that oxygen. And in order to oxidize this, we get another molecule of pyridine. This will now act as a base again, remove this proton, and form a double bond between that oxygen and the phosphorus. Okay, so what you'll end up generating is this group here with now a phosphate backbone. Okay, so that works really well. It's highly efficient, and that's how the oxidation goes. So once we generate that phosphate, we can now repeat steps 1 to 5 with base 3, and then repeat steps 1 to 5 with base 4, etc., etc. So you can see that this is an iterative process. Yields are really good for 30, probably upwards to 40 nucleotides or so. It really depends on how good your yield is with that coupling step. So even if you have a coupling of 98% or 97%, that can have a huge impact on your overall yield. And then as soon as you start making longer oligomers, then you can get lower yields. Okay, so it's important to make sure that chemistry is really fully optimized. One thing I should note, and I will just go back, just a couple slides back, just to show you what is really important for making sure that you get a good yield. Yeah, so this is step 3 during the synthesis. So things that can compete with this reaction are moisture, right? So if you have moisture in the air, water is a competing nucleophile that can therefore react here. It's a much better nucleophile because it has no steric hindrance really whatsoever. So it's really important during this chemistry, and I'll show you a picture of a machine, is that we use anhydrous solvents, so solvents that don't have any moisture in it, and we do these under argon or nitrogen gas, so that moisture from the air does not compete with this reaction. So on hot, humid days, even in a controlled fashion, we try to avoid using the synthesizer because inherently just a little bit of moisture in the air can compete with this reaction. Okay, so once we do this and we generate our oligonucleotide, and here I'm just showing a tetramer, we need to remove a few things here. We need to remove this from the controlled pore glass resin. We need to remove the O-cyanoethyl groups from all of them. And we also need to remove the benzoyl protecting groups. Seems like a lot of work, and it definitely is. But fortunately, there's one step needed that can do all of these things simultaneously, and that is ammonia. Okay, so ammonia can come and react, remove the benzoyl group, remove the O-cyanoethyl group, and remove this from the CpG resin. Ammonia, as you know, is a gas. So what we use is a hydrated form, ammonium hydroxide. And we typically do this at 55 degrees. And usually we do this overnight for 16 to 18 hours. And then the next day we have a beautiful DNA RNA strand with all those protecting groups off. So let's look at each of those 3 steps of those deprotection steps. So removal of the CpG from the solid support. Okay, so how does that work? So I'll kind of draw what that CpG looked like. Okay, and R is your DNA. Okay, so I'm not drawing the DNA, but this is what it looks like. So you have an ester and you have an amide. Okay, so really what happens is that it's fairly straightforward. Your ammonia will come and react at that ester to form a tetrahedral intermediate. So it's simple nucleophile, electrophile coming together. Okay, and then here you can have another NH3 group, which can now act as a base to simply do a proton transfer. You still have that tetrahedral intermediate. And then what you're going to do is you're going to collapse a tetrahedral intermediate, form a double bond here, and then this will come off as OR minus perhaps, and then this can pick up a proton from the conjugate acid of ammonia to give you your DNA. Okay? You could also have this come down and then this picks up a proton from the conjugate acid of ammonia to generate the product too. So I've just done it over 2 steps. You could do that step over 1. Okay, so that's one thing. The second thing that's going to happen is the removal of the ocyanoethyl groups. Okay, so here we have our ammonia. This one is a little different. So we've seen ammonia act as a nucleophile, but as we've shown with the proton transfer step, it can also act as a base. So what you have attached to this cyano group here are a couple of protons. And normally carbon hydrogen protons are not very acidic. However, because they are adjacent to a good electron withdrawing group, you can push electron density into that nitro group, therefore making those protons here fairly acidic. So if you do that, you generate this intermediate like I've shown, and then the electrons will come back, form a double bond here, and then you'll break this carbon-oxygen bond to give you your desired phosphate without the protecting group. And your byproduct is this molecule here, which is small and volatile. So this will come off under reduced pressure. This is known as an elimination reaction through the conjugate base. So you can see first we eliminate, generate the conjugate base. Okay, this is the conjugate base. It's simply acid-base chemistry. And then the conjugate base moves its electrons to remove that. So it's not an E2 mechanism. It's elimination via conjugate base. And then finally, removal of the benzoyl groups. So this is done, I'll just take one of the examples. And ammonia will come, and it's fairly straightforward. You'll get the NH3 attacking that carbonyl group, which is electrophilic. Okay, so now you have a nitrogen with 4 bonds. Do a proton transfer like we did at the beginning. Now you have your tetrahedral intermediate. And now this will come down, and then this can pick up a proton on the way out, most likely from the conjugate acid of ammonia. And then what you are left with is your deprotected exocyclic amine. So this will work. I've shown the example with cytidine, so it'll be analogous to adenine and guanidine as well. And you can see that your deprotected byproduct as a result will be this compound here, which again is fairly small, and you don't need to worry about. It'll come off under reduced pressure on the rotavap. So here's an overview of the cycle, and I like this cartoon here because it really literally shows the cycle, how it works in a cyclic fashion. You can think of it like from this perspective. So cycle entry is when you immobilize it, you detritylate, as we've seen before, right, with 3% TCA. Then you couple with the phosphoramidite, and then you do the coupling reaction, right? You need tetrazole or something similar to that. And then at this stage here, you do a capping step, and then you do the oxidation, okay? So 3% TCA. Here you need to use tetrazole. And then for the capping step, you need to use acetic anhydride. And the oxidation step, you use iodine, water, and pyridine. Don't worry about this at the moment. There are instances where we may want to alter and modify the oxygen with something like a sulfur. We'll talk about those benefits another time. But for now, just focus on this main pathway. So you repeat this, and then cycle exit is when you use the ammonium hydroxide to release everything off from the resin and all those protecting groups. This is a picture of what a machine kind of looks like from the inside. And I just want to highlight a couple of things here. We have these little cartridges that we can purchase, and inside is the control pore glass bead. So you fasten it to the machine, and then you can push solvent through, and then there's a frit that doesn't allow any solids to go through. So you do all the reaction on the bead, and then you can rinse through. And then you have vials here for all your phosphoramidites that you can purchase. And then you have solvents like acetonitrile. Again, it has to be anhydrous. Iodine, acetic anhydride, tetrazole, your coupling agent. And then this is always done under argon or nitrogen gas, okay, to keep it under an inert atmosphere. This is another depiction. This is from your textbook, and this is just, again, another way to look at the cycle. So, again, it's the same type of thing, right? Detritylation, step 1, addition or coupling, step 2, capping, step 3, oxidation, step 4, okay, and then deprotection, and then if you're done, then you cleave it, okay. But you can see here that it's sort of a cyclic fashion here. Okay, so definitely go through this so that it makes sense. It's just drawn a different way from the other cartoon that I showed. Okay, so in the last few minutes, I just want to spend some time now thinking about RNA synthesis. And so far we've made DNA using DNA phosphoramidites. And I hope you enjoyed that chemistry. But what about RNA synthesis? With RNA synthesis, the only difference, right, is we have this 2' hydroxyl group, which is not around in deoxyribonucleosides. So from a chemical point of view, we need to think about how we are going to deal with that 2' hydroxyl group. This 2' hydroxyl group is going to cause some problems because we need to protect it, because if we don't protect it, you can imagine this 2' hydroxyl group will react with other phosphoramidites, and then you'll get side reactions. Okay, so we have to protect it. We got to protect it in a way that it does not become removed during this catalytic, or not during the synthetic cycle that we talked about. So it can't come off with weak acid. And when we're using things like iodine and pyridine, those are basic conditions as well. They're not super strong basic, and the acidic conditions are not super strong either, but it has to be robust to mildly acidic and mildly basic conditions. And then later on, we need to find a unique way to remove it from the structure without compromising any other functional groups. So those are the problems I just talked about. We need to find a way to selectively protect and deprotect the 2' hydroxyl group. So a really good way to do that is to take the 2' hydroxyl group. So imagine this is a 2' hydroxyl group, and we treat this with a silicon protecting group. Okay, this silicon protecting group is called tert-butyl dimethoxysilyl chloride. A little bit of a mouthful, but some of you may have seen this before. Tert-butyl dimethoxysilyl chloride. This is often abbreviated as TBDMS. Or TBS chloride. Okay, so if you take this compound in the presence of a base, you can very easily protect that 2' hydroxyl group with a solid protecting group. Silicon is very oxophilic. It really likes oxygen very much. So if we're going to design phosphoramidites, we need to realize that we have to incorporate some type of 2' TBDMS group at that position. And why don't we start with uridine as an example. Uridine doesn't have any exocyclic amines, so we don't need to worry about benzoyl protecting group. So our strategy is going to be as follows. The first thing we're going to do is protect the 5' hydroxyl group with the DMT chlorine group, which you've seen before. And then before we make that phosphoramidite, we need to protect the 2' hydroxyl group. And we do this typically with TBDMS, chloride, and base, and then we can get this compound here. And then once this is made, we can create that phosphoramidite just like we had done previously. So we can take our chlorophosphoramidite, how is the structure drawing coming along? The more you draw this, the easier it gets. And we need some type of base for that as well. So that's how we make our phosphoramidite. So we have an extra step. The yields are not as, the TBDMS, the yields are not as good during the phosphorylation because you might have some steric hindrance from this group preventing that reaction from occurring at the same levels as it would for deoxy nucleotide. And furthermore, you can also get TBDMS incorporation at the 3' position, and this would be a undesired product. It's typically the minor product. But what you need to do though is you need to separate these on chromatography, and you can imagine these have very similar polarity. They're isomers of one another. There's this 2' hydroxyl group is a little more nucleophilic because of something known as sugar puckering. It adopts something called the C3' endo conformation. You really don't need to worry about that at the moment, just kind of foreshadowing 5-membered ring conformations later on in the course, the next course. But what that means is that this 2' hydroxyl group is oriented in a more nucleophilic downwards position, and the 3' group is shielded more upwards. So that's why you get this one as your major product, this one as your minor product, but nevertheless, you still need to separate that. So that reduces overall yield and the efficiency of the reaction. But we don't really have a choice because we can't have that 2' hydroxyl group. So the solid synthesis of RNA actually is that 5-step cycle that's identical to DNA. So you treat things exactly the same. You don't need to change anything whatsoever. The only thing that differs is the end step, in which you do the deprotection of the RNA from the solid support. So everything remains the same. Even the deprotection, actually, it's just what you have to do after the deprotection. Okay, so here's your strand. And I'll just draw an example base with a protecting group. Okay, so the mechanism and how this all works in terms of removal from the CpG and the exocyclic amine, the O-cyano ethyl group, remains the same. You treat this with ammonium hydroxide at 55 degrees. Okay, so then you generate your RNA that still has that silyl protecting group attached. And at this stage here, we're going to use a very specific chemoselective reagent to remove the silicon protecting group. And we're going to use fluoride anion. And typically we use tetrabutyl ammonium fluoride. Okay, also known as TBAF, and it's a great source of fluoride anion. And what will happen is that this F- will deprotect the silicon, and you will get removal of that 2' hydroxyl group, or the 2' protecting group, to now have a 2' hydroxyl group. Okay, so it's really just one additional step after the deprotection. All right, and typically the yields are pretty good for that. Yeah, so that concludes chemical synthesis of oligonucleotides. So I think I'll just write a couple sort of conclusions based on part A, part B, part C. So part A, we talked a little bit about the properties of RNA, like nucleotides and the monomers, and we looked at some of the synthesis and building blocks. So I'm just going to say that, oxonium or oxocarbenium intermediates. Okay, so these are these structures that look like this, were likely used to prebiotically synthesize nucleotides. Okay, so this type of intermediate afforded an electrophilic form in order to get reactions to happen at that 1' carbon. Number 2, we looked at the enzymatic biological synthesis. The big take-home message from that, it occurs in the 3' to 5' direction. Three prime to 5' direction for polymerase-driven enzymatic synthesis, and then this unit, which is the chemical synthesis and took, of course, the most time. We had to talk about protecting groups and analogous to peptide synthesis. Protecting group. Strategies needed for chemical synthesis. And synthesis occurs in the opposite direction from biological synthesis. So the 5' to 3' direction. Okay, so that concludes part 2 for sugars and nucleic acids. See you soon for part 3. Take care, everyone.